Well, we've now reached the point, having looked at hope from a couple of different points of view. We know that hope has something to do with neurotransmitters and neurochemicals. And we've looked at some of the literature and data that are available to make that case. But today, we're going to take sort of the opposite point of view. Namely, we're going to look at hope as a biological, biochemical, neurological issue, but primarily when it's not there. Hope defined as the lack of hope. So we'll have a joyful discussion about the neurological definition of hope. We'll then go on to talk about the lack of hope, sometimes manifesting in depression, sometimes manifesting in hopelessness. And then lastly, we'll take up the role of the underlying neurochemical that is associated with the state of being hopeless or depressed, and that is the neurotransmitter / neurohormone serotonin. So as I intimated moments ago, it's sometimes easier to learn about a complicated thing like hope that has many components to its realization by looking at the lack of it. What things are in play? What neurochemicals, what neurotransmitters are in play when one is in a state of lacking hope or hopelessness? So sometimes it's more illuminating to learn about hope or try to put the pieces of the hope puzzle together by discussing what it means when hope is not present. Now, we go back to the aphorism that where there's life, there's hope, suggesting that hope is an underpinning of a healthy life. And we know that that link is of ancient origin, that we had this idea in our species going back millennia that there was a link between a healthy mindset and a hopeful one. So we have that persistent idea that is found in many of our representations of hope, whether they're artistic or literary or other. And we know that while we haven't had a good understanding of the neurochemistry and neurobiology of hope for very long, we know that even many centuries ago, the connection was made between having hope in your body as a human being and the idea that somehow hope was emanating from the brain was alive and well. And to the best of my knowledge, the earliest explicit representation of hope as something coming from the brain goes back to the Middle Ages, specifically 980 AD, where a philosopher, whose name I will not try to pronounce, but it's there for you in the third bullet, Hussein ibn Abu Ali, or, well, I'm trying to pronounce it now, Ibn Sina, was born in Uzbekistan and became a philosopher who had medical knowledge and interest, and he specifically identified sickness in the body as originating in the brain, and furthermore intimated that hope or lack of it was connected to the status of the body, the health status of the body. So the idea that there's a link between the brain and hope and wellness goes back over 1,000 years, as far as we can tell, and in the interim, we've collected a lot of information and a lot of data to support the notion that hope is essential to one's health, and we now know that hope is, at least in part, a neurochemical event. We furthermore have modern studies that clearly show that a state of hopelessness sometimes attends illness, and in the case of severe illness resulting in severe hopelessness, particularly in things like cancer, we have this sense of giving up, of finally resigning oneself to one's fate and not attempting further interventions to achieve wellness or a state of helpfulness as a result of giving up on hope and one's own existence. So we have this other way of looking at there being a relationship between hopelessness and mortality. Now, neurochemically, we already know a little bit about this. We know that hope exists in the body as a result of having the correct balance of neurohormones or neurotransmitters. And recall that these neurochemicals can simultaneously serve both as a neurohormone and a neurotransmitter in many cases. So our ability to respond appropriately to stimuli going on within our environment and to do so within specific prescribed homeostatic ranges is dependent upon having the correct balance of those neurohormones. Now, what are they? Well, at a minimum, we're talking about the following: dopamine, epinephrine, endorphins, and serotonin. There are several others we could add to the mix, but we won't, at least today, because we want to keep things sane. And it gets really complicated. But these are the main ones about which we have data and about which we would make the argument that we need these materials in our bodies in the correct amounts to impart a healthy, neurochemically based mindset. We also know, and we'll discuss in the next module, that there are connections that are genetic, that can vary with a person or between people because of differing genetics, and the mindset, whether it's hopeful or hopeless, that emerges is certainly for an individual dependent on one's life experiences. And again, we'll talk about that in much greater detail in the next module. You will find, as we discuss this, and perhaps even in your own life you've had some experience with these phenomena, that there's a fair amount of play in the terminology, and that ideas and terms get batted around without a whole lot of definition attached to them. So two of the terms that you might hear in this context are depression and hopelessness. Now, they're not the same thing. And it probably is not correct to say that hopelessness is just an extreme form of depression. It's really not. There are different underlying characteristics that separate the two, but they are probably both somewhere on the spectrum of well-being, and as a consequence, it's easy to conflate one with the other, even though they are distinctly different definitionally. There was an interesting study that correlated hopelessness with mortality. In other words, people who were hopeless died at a fairly significant rate once they achieved that psychological state of hopelessness. So there's the correlation of coefficient for those two phenomena, hopelessness and mortality. It's not particularly high, but it's high enough that it is concerning. Now, if we were going to separate these two ideas, hopelessness and depression, we would say that hopelessness is more of an enduring, that's a very important word, enduring cognitive set that interferes with, at a minimum, appraising new situations. In other words, we all get hit with things we haven't seen before, just on a daily basis. And if you're truly hopeless, then it's impossible for you to deal with new stuff that you haven't seen more. Furthermore, there are major impediments in one's ability to find and exercise coping mechanisms if you are truly hopeless. You simply are weighted down, freighted by the many things that are leading to your state of hopelessness that that interferes with your ability to raise the necessary energy and effort to cope with new things that are difficult. And that's what we see in a genuine state of hopelessness. Depression, on the other hand, is very debilitating. I'm not saying anything against that, but it is a less stable set of conditions. It's a mood more than an enduring cognitive set. Again, I'm not saying that depression isn't debilitating. It definitely is, but it is definitionally separable from this thing called hopelessness. So there are a number of studies that have looked at hopelessness and also depression, some in the same study, some in different studies. And there's sort of an emerging consensus, particularly in the studies on hopelessness, that the state of hopelessness is one in which the individual feels a sense of doom, that it is the end, that all is finished, that nothing can be done. And often this state of hopelessness is exacerbated by or accompanied by this notion of giving up, which is a whole complicated complex of behaviors that includes many negative sentiments, such as a depreciated self-image. I'm worthless, for instance. The individual who's hopeless secures no gratification from human relationships, gets no boost or connection from others that is salutary in nature, and as I mentioned previously, shows a failure of previously existing coping mechanisms that used to allow for a relatively normal life. Well, in hopelessness, those coping mechanisms are gone, and you're simply buffeted by the winds of everyday life and find it very difficult to rise to the level of energy and self-appreciation necessary to combat all of the things that are going wrong in one's life. Now, I like to illustrate the concept of hopelessness by referring to a particular historical event. I've already mentioned it to you early in the course, and that would have been the bubonic plague. And this is a quote taken from that time from the chronicler Agnolo di Turo, who wrote, among other things, A Plague in Siena, in which he wrote fairly extensively at the time about the plague as it hit Siena in Italy. And this is one of the quotes from that chronicle. He said, quote, "They died by the hundreds, both day and night, and all were thrown in ditches covered with a little earth. And as soon as those ditches were filled, more were dug. And I, Agnolo di Tura, buried my 5 children with my own hands. And so many died that all believed it was the end of the world." Okay, so this is a horrible situation. People are dying all around you. You don't know if you're next. Your family may have preceded you in death. You may have, as Titura did, you may have had to bury them with your own hands if they got buried at all, because so many were dying. They couldn't keep up with the ditch digging. People were afraid to dig the ditches. People were extorting lots of money from the living to bury those that they could. You could leave your loved ones in the morning and find them expired by evening if they got a particular form of the plague, known as the septicemic plague. It was not atypical to have to bury your own children, which most people consider a very unnatural state to predecease your children. And this happened so extensively and for so long that literally everybody believed in their hearts and in their minds that the world was coming to an end and that this was Armageddon writ large playing across the landscape. And so this is sort of a good historical representation of what human hopelessness might feel like. These are some images that were developed during the time of the Black Death. On the left, you see the art form known as the Dance of Death. And in it you see the dancers represented by skeleta with human features performing these dances. If you look closely, you can see garments still attached to the skeleta, and the notion that this is supposed to convey is that some of the garments on the skeleta are of upper class origin, some are of lower class origin, and what this is supposed to convey is that death will take everybody, the rich and the poor alike. You can't escape. This is your fate. You will die this horrible death in the time of the plague. And then we have literal representation of that in the right photo. You see dead people amassing in the streets because there aren't enough people to bury them. And as the ditches get dug to bury the dead, more are immediately needed. They began simply creating large trenches in which bodies were laid stick style, one head at one end of one individual, feet at the other end in the same row, and it was just horrible. And they would cover the one layer of human bodies with a little bit of dirt and then start the next layer right on top of them. They were that compressed. And you can see that some individuals in this painting have their clothes covering their mouth, trying to escape the stench of dead bodies. Others simply go on about their business, but you can see that there are dead people accumulating in doorways, dead people accumulating in the streets. You can see that children and infants are clinging to their dead mothers. It's just a horrible, horrible time. And perhaps this is what human hopelessness looks like. So there has been a long-standing relationship between hopelessness and mortality. The plague is not the only historical representation of this. There are others, but it's the one that I know the most about, so I bring it up. But I think we could agree that hopelessness perpetuates depressed feelings and the psychobiology of those people who are hopeless to extreme levels. Among other things, hopelessness and indeed depression can weaken one's immune system, and this exacerbates the toll on the human body. If your mind and your body is depressed or hopeless, your immune system also takes a hit and is not as effective at warding off pathogenic agents and correcting body processes that are not behaving at their optimal levels. So there is a demonstrable mind-body connection between hopelessness and illness. What can we say about some of the neurobiological aspects of hope and hopelessness? Well, there was an interesting study by Gottschalk and some colleagues taken in 1993. They were using PET scans. We'll talk about the details of this in a later module. But it's one of those kinds of body scans that can reveal graphic information about what's going on inside the body. The particular study used 10 male volunteers, and the volunteers were asked to, on the one hand, think about something that was thoughtful, and on the other hand, think about things that were, they were asked to think about things that were hopeful versus things that were hopeless. And while they were doing this, the PET scan was running and pictures of their brains were being detailed. And these were correlated with thoughts that they experienced while doing readings on the PET scan. So what they discovered, what the take-home message from this particular study was that hope and hopelessness activated different parts of the brain. So that leads to the idea that there's a separation between the concept of hope and hopelessness in the human brain, and therefore would be expected to have different impacts on the human body. So as we descend into the complexity of this issue, we're going to be talking about biochemistry of hope and hopelessness. We know that some biochemical states, and here we're largely talking about neurohormones and neurotransmitters, some combinations lead to hope and a sense of well-being. Other combinations lead to a hopelessness or depression. In some extreme cases, we may evidence of suicidality. So it's important in making these descriptions to note that these are all complicated states of mind that are not due to a single cause, but due to many interacting causes. Recall I said earlier that, yes, we're going to be talking about specific biochemical states, but that there are also underlying genetic issues that are important. And so, in addition, we have a third category of relevant factors, which would include one's life experiences interacting with the genetic ones and the biochemical ones. So it is a very complicated situation. We don't want to oversimplify it, but we do want to see if we can at least tease out some of the major players and learn something about their individual impacts so that we begin to get a sense of what a hopeless versus a hopeful mindset would look like. So let's talk about some more of the important underlying neurochemicals. Endorphin is one. We've already talked about it as a natural painkiller, which on a weight-for-weight basis is 3 times more potent than morphine, which you probably already know as an opiate drug. We know that endorphins, among other things, can affect the amygdala, and when it does this, it tends to lead to a pleasurable sensation. This is where chocolate and we get the runner's high, and the pleasure of sex and cocaine are attributed to endorphin interacting with the amygdala. It's also probably the underlying basis for a feeling of ecstasy, as we'll discover when we talk about religion. And both of these things, or all of these things, are an offshoot of hope. Other important neurotransmitters contributing to a sense of well-being would include dopamine, which we've already described as the I feel good substance. We know that it's produced and released by various parts of the brain, including the substantia nigra. We know that it's important in the proper operation of the nervous system. We know that various degenerative nervous system diseases, including Parkinson's and Huntington's chorea, are involved with low dopamine levels or an incorrect distribution of dopamine, and that our healthy emotional responses depend upon having dopamine at the right levels in combination with endorphins, both of which can act upon the amygdala to produce a sensation of well-being. We've met dopamine before. Let me remind you that in Helen Fisher's rendering, dopamine is responsible for one of the 2 stages of love, for high levels of infatuation in the event of new love, a sense of joy and self-confidence and motivation during that period of attraction. Dopamine is also associated with euphoria, as I mentioned. It affects the amygdala, and that's where we get this sense of joy at the event of new love, and a sense of sleeplessness when you're focusing on the beloved one, as well as a loss of appetite. We know that dopamine is active all over the human brain, that it has at least 4 major neurological pathways in which it has impacts, and there are at least 5 different kinds of dopamine receptors in the nervous system. Again, we saw dopamine when we talked about Helen Fisher and the attraction phase of love, which eventually yields to a different hormone, oxytocin, and the maintenance phase of love. We also know that low dopamine can lead to an inability to respond appropriately to happy events, to lack of motivation, and a lack of self-confidence. So all of these are the kinds of information we have obtained from a variety of different studies on dopamine and human beings. And now we get to another extremely important neurotransmitter slash neurohormone and the healthy, neurobiologically healthy human being. And this is the element known as serotonin. It is yet another neurotransmitter slash neurohormone. And to be a happy, well-adjusted person, you need to have serotonin in your system at a specific threshold. If it goes below that threshold, you don't have this happy feeling. So serotonin is important in calming anxiety and also relieving or preventing depression. Low serotonin is associated with mild to moderate depression. It is also associated with anxiety, fear, a sense of worthlessness, apathy, insomnia, and fatigue. Now, all of these things are symptoms of depression. And it turns out that serotonin is one of the few things that we can reliably manipulate in the human body to relieve those symptoms of depression, and thus has become the focus of therapy for depressed people. As far as we know, there aren't any major clinical presentations that happen as a result of having serotonin levels that are too high. So we are not aware of a downside to having serotonin levels that are higher than that which would be considered normal. However, if serotonin levels are too low, then we can get the negative things that I just described. People with low serotonin levels lapse into negative feedback cycles of struggle and sometimes hopelessness. So there are many clinical studies that show when serotonin levels are too low, lots of bad things start to happen. And these bad things include reclusive behavior, inability to handle stress, inability to handle conflict, excessive worrying about trivial things, sort of obsessive-compulsive disorder, impulsiveness, obsessive cleaning, another OCD kind of symptom, heat intolerance, panic, phobias, insomnia, and sometimes just a pervasive sad feeling. So these kinds of symptoms can be present in the case of low serotonin. They may not all be present. Many of them may be present simultaneously. The clinical evaluation of this condition is very complicated. But we do know that serotonin is very important as a neurotransmitter and neurohormone. We know that serotonin is made in the brain, but about 90% of serotonin's activity occurs somewhere else in the body. And of course, that makes it a very good neurohormone because it's made one place and it has activity elsewhere. We know that these cells that are responsive to serotonin's neurohormonal activity are distributed all over the body, but it includes major functions in places like the gut and even blood platelets. So this is obviously neurohormonal activity rather than neurobiological activity. We know, though, that 40 million brain cells have the capacity to respond to serotonin as a neurotransmitter. We also know that serotonin is really important in some of the autonomic nervous system functions, such as heartbeat, muscle contraction, and various endocrine functions. So it's a neurohormone, neurotransmitter with very diverse activity all over the human body. And we also know that serotonin can profoundly influence human moods in ways that are good and bad. When serotonin is too low, it can lead to depression. And one hypothesis about how this happens is that stress itself may reduce the production of serotonin, causing the bad results, bad behavioral results that are in evidence in many people who are depressed. But we can't measure serotonin levels in the brain. We can only measure serotonin levels in the blood. And so what we do is monitor levels of serotonin in the blood with the finding that depressed people have lower serotonin levels than people who are not depressed. But we recognize at the same time that the influence that serotonin is having on those moods is largely neurobiological, largely taking place in the brain, but we cannot measure directly serotonin levels in the brain. We can only do it in the blood. And so what we're doing is measuring a proxy by which we're inferring levels of serotonin in the brain. I would add that there are a bunch of studies on serotonin levels and associations with negative impacts, but the number of individuals in these studies is often quite low, which mitigates against a good statistical analysis, and as a consequence, we have lots of studies with inconsistent results. However, there is general consensus. Well, consensuses are always general, so I shouldn't say that. There is consensus that serotonin is acting as a neurotransmitter and that low serotonin levels are at least correlated with depression. Now, how does serotonin exercise this function? Well, it's a good neurotransmitter, just like the other ones we've discussed. So we know that serotonin is contained in vesicles, which reside at the terminus of axons, and that when an action potential reaches the end of that axon, the serotonin vesicles will fuse with the axonal membrane, and serotonin is thus released into the synaptic cleft. Thereafter, the serotonin diffuses across that synaptic cleft and binds to dendritic protein receptors in the postsynaptic neuron, thus initiating a new action potential in the second or postsynaptic neuron. But here's a difference between serotonin when it acts as a neurotransmitter and other neurotransmitters. Once serotonin has done its job, namely binding to that dendritic postsynaptic neuron and initiating a new action potential, it lets go of that dendritic protein receptor on the postsynaptic neuron and re-enters the synaptic cleft. And at that point, the serotonin is taken up by the first neuron, by the axon that released it, and gets recycled. So this is a difference from what we discussed before. Other neurotransmitters are simply broken down. They let go of the postsynaptic neuron and they re-enter the synaptic cleft, but they're broken down by an enzyme so that they go away, basically. Serotonin, on the other hand, gets recycled. So it's taken up again by the first axon, the one that released it, and it gets repacked into synaptic vesicles so that it can be reused and released again in response to an action potential. So again, recall all of this is going on in the synapse, the space between two neurons, and what's going on is that vesicles filled with a neurotransmitter, in this case serotonin, will fuse with the axonal membrane, as you see right here. This releases the neurotransmitter, in this case serotonin, into the space between the two neurons. The serotonin diffuses across this gap and binds to a specific dendritic protein receptor in the postsynaptic neuron. It initiates a new action potential in this second neuron, but then it will let go of this receptor and re-enter the synaptic cleft. As I mentioned previously, most neurotransmitters will be degraded by an enzyme after they do this, after they re-enter the synaptic cleft. But in the case of serotonin, what happens is the serotonin gets taken up by the first neuron and repackaged in these vesicles so it can be used again. So this is important in terms of treating depression, because if stress causes depression, and if the serotonin levels in the brain are low, we could potentially intervene by artificially increasing levels of serotonin in the nervous system to compensate for the fact that stress is causing a reduction in the creation of serotonin in the nervous system. In other words, we can use drugs to manipulate the situation in such a way that we artificially increase the levels of serotonin in the nervous system. So you remember that I said a couple of times that after serotonin binds to the dendritic protein receptor of the postsynaptic neuron, the serotonin is released from that receptor, re-enters the synaptic cleft, and then gets taken up by the first axon that released it. In other words, it gets recycled. And this provides us with a basis for artificially increasing the level of serotonin and thus producing a sense of hope, which is drug-based in the nervous system. And we do this by preventing that recycling which takes place naturally. We have specific drugs that can do this, that can prevent the reuptake of the serotonin once it gets back into the synaptic cleft. And these drugs are named selective serotonin reuptake inhibitors, also known as SSRIs, because that's way shorter. So here's our first neuron, and here is the axonal end. We see the serotonin-filled vesicles here. We have one serotonin-filled vesicle fusing its membrane with the axonal membrane, and it's releasing the little molecules of serotonin into the synaptic cleft. And you know already that what's going to happen is that the serotonin molecules diffuse across the cleft, they bind to dendritic protein receptors in the postsynaptic neuron, and eventually result in a new action potential being initiated in this second neuron. Then, once that's done, the serotonin molecule separates or disengages from the dendritic protein receptor of that postsynaptic neuron, and it will now diffuse back across the cleft towards the first neuron, and the molecule will now enter this gate, which allows the serotonin to specifically pass through, because it has the right shape. So the serotonin molecule will re-enter the first neuron, the one from which it was released, and it will now get repackaged in a membrane so that when a new action potential comes along this first neuron, it can reuse this serotonin as a neurotransmitter. So that's what would happen normally. But if we have a serotonin selective reuptake inhibitor present, which in this graphic is represented by this little plug shape that is adorned with a P, this is the SSRI molecule, and when it's present, it will come over here to one of the receptors, and it will go into the gate and plug it up. And in this plugged condition, it's blocked. The serotonin molecule can come over here, but it can't bind because the space is being taken by this SSRI molecule. So the serotonin molecule is not taken up into the presynaptic neuron, as it normally would be, but instead stays here in the synaptic cleft, where it can continually bind to the dendritic protein receptor of the postsynaptic neuron, initiating new action potentials in it. And that's how we correct for low serotonin in depressed people. We give them a drug called an SSRI to block the channels through which serotonin would be taken up by the first neuron, the one that released it, and repackaged. We stop that with the SSRIs by plugging the channels through which the serotonin would enter the first neuron. And in the plug state, it forces the serotonin to stay in the synaptic cleft and to keep binding to the postsynaptic neurons. So that's how they work. And here's a written representation of that. The SSRIs enter the synapse. They block the serotonin reuptake channel in the presynaptic neuron, which means that once the serotonin is released by the first neuron, the levels in the synapse of serotonin won't go down. And this means that the postsynaptic neuron will be continually stimulated, and that potentially has the ability to relieve symptoms of depression if that depression is due to the biochemical situation of low serotonin. We note that SSRIs do have some side effects. They may cause increased anxiety initially, but usually people can adjust to that. And I would also like to note that eventually the serotonin that is now forced to stay in the synaptic cleft, eventually the serotonin will be degraded by enzymes called MAO inhibitors. So you're not forced to operate on excessive serotonin levels indefinitely. But there is a lag between that, the degradation, and the release of more serotonin, so you can regulate the serotonin levels in the cleft with a reasonable degree of reliability, allowing the amount of serotonin to stay in a therapeutic range, even though it's being degraded by the MAO inhibitors over time. And here's your study guide for this module on serotonin and artificial hope.